All right, everyone, welcome back. This is going to be another one of the sample section 3 walkthrough videos. I haven't done one of these in, I think, a couple of months now, actually. They take a little while to put together because I've got to obviously write the questions, and that's a pretty time-consuming process. And I do try to get as many videos out every week as possible. Usually my turnaround is kind of like a couple of days, and then these usually take a little bit longer. Truthfully, this one, though, I've worked on just today, actually. This is like, what time is it? 7 o'clock almost on Friday night. I've kind of worked on this throughout the day amongst a bunch of other things. My schedule's all over the place. What I've done is made the stem pretty long. So there's 7 questions. So normally I kind of have a couple of stems in these videos. This one's just going to be the one stem, so we can just focus on the one topic. And again, it'll be kind of a mix of how I go about problem solving, how I would reason out the answers, but then also there might be little points of theory. So it's kind of redox focused from chemistry. So if that's something that you're a little bit concerned about, then this could also be good. I do cover all of what I think is relevant theory in the chemistry crash course videos from last year. So if you haven't already seen those, check those out as well. But yeah, this is a little bit more strategic, a little bit more looking at problem solving and how to kind of navigate complex information, basically. And I should say as well, these are all original questions from me, and I think there should be a bigger resource of free questions because, as you know, I'm pretty outspoken and against the whole idea of paywalls for question banks, which is what most of these overpriced courses do. I don't mind the idea of tutoring, but I really don't like the idea of a prepaid course where you're effectively just paying to get access to theory. And a lot of the questions, from what I can tell, is kind of junk too. So hopefully this doesn't fall into the category of junk. It is free, but it doesn't mean that it's low quality. I put as much effort into this as I would if I were to be paid for it effectively. So yeah, hopefully you guys are getting a lot of value out of it. So first of all, we've got below is a table containing the potential oxidation states of 4 metals W, X, Y, and Z. Obviously these don't represent actual metals on the periodic table, it's just theoretical. And then we've got metal oxides are the result of oxidation of metals in certain redox reactions. So, you might already be familiar with that concept. Metals can also bind to other anions called ligands to form metal ligand complexes or coordination complexes. So if I was breaking this down, I should say as well, I forgot to mention because it's been a while, these are all on my resources page, which is linked below. So you can actually pause the video and give them a go first and then use this as a worked solutions video, and it'll be linked on the page at the top as well, so you can watch it straight from there. Here I can see a definition. So immediately, if you've done first year chem, then you'd already be familiar with what metal ligand complexes are, but you may have gone hazy on it as well. And if you're non-science, then this might be brand new. So we just want to know, okay, metals can bind to other anions. So a metal that's usually positive can bind to an anion, let's just call it A negative, just in general terms. And it can form a metal ligand complex, which is also going to be called a coordination complex. So we've got a synonym and we have to watch out for both of them in the questions. An example of a coordination complex is shown below. So we can see a metal with 6 chlorides attached to it. And it says this particular coordination complex has 6 ligands. Now we're getting a better sense of what ligands means, attached to the central metal M, and therefore has a coordination number of 6. So now we're getting into more technical terms. So coordination number is technically just equal to number of ligands, or if you wanted to use non-chemistry terms, number of attachments, basically. And then it has a formal charge of 3-, shown here. Metal ligand complexes can also bind to other oxidized metals in the same way that oxides can attach to metals to form metal oxides. And metal oxides can be classified as being of the nth degree, so a bit of new information here, where there are n metal ions per metal oxide molecule. So again, for non-science, that's a bit of a mouthful. But if we just took something like, for example, MO2 as a metal oxide formula, the idea is that this here is the number of metals shown. There's just one of them. Whereas if it were instead something like M2O3, that would have 2 metals per molecule or per compound. And I've put in an example because this is the kind of thing that I see ACE doing as well. Whenever they give something really technical, they always give an example to kind of clarify the meaning of it. So for example, sodium oxide, Na2O, is a 2nd degree metal oxide. It has 2 metal ions in it. The same system can be applied to metal ligand complexes as well. And so we get into the questions, and we might be bouncing back to the info as well. So with question 1, given the following chemical reaction, where M and A are unknown species of metal, and you can see them appearing here, 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 and here. We've got to work out metals M and A could be which of the following from the table. So from the table, I can see that it only gives me oxidation states. So this must be my tool to work out which ones are which. So if I look at each of them, I have to work out the oxidation numbers, right? So we can do this algebraically. If we take the first state here, metal M, then we don't know what state it's in. So we just put M plus hydrogen, which is always in the +1 state, plus, and then carbonate here is in the -2 state. Now, if you're from non-science and this is a little bit confusing, I would say it is worth memorizing a few of the very common ions and their charges, but there's a possibility that ACE would actually give that to you in the STEM information as well. So we put all this together, that should add up to the formal charge on this compound, which is 0, like this. And so then we end up with M plus 1 minus 2 equals 0, and so therefore M minus 1 and M equals +1. So that means that metal M is in the +1 state here. Over here, you've got AO2, so an oxide of metal A. So again, the same thing, A is unknown, plus 2 oxygens, which are in the -2 state. That cancels out to 0, so we solve that, we get A is in the 4+ state, like this. And then over on the other side, we have to check what states are possible over there. But what we'll find here is that in this case, it's not actually true redox, they're not actually changing their oxidation numbers, they're staying the same. So we've got 2 lots of metal M plus an oxygen, cancels out, and then we get, when you solve all of that, I'll cut some corners here, +1. And this one over here, hydroxide, has a -1 charge, so A plus 4 lots of -1 adds up to 0, so A comes out as +4, like that. So the states in this case are +1 and +4. And then it says metals M and A could be. Now it doesn't use the word respectively, so it doesn't mean that the first one has to be the first one, so to speak. It could be one way or the other. So I would just go through each of the options and see which is likely, because they're very specific. Whenever the answers are like really specific to one statement, it's easy just to follow what they're saying rather than trying to anticipate it, because there's too many different variables. So metals W and X. So if I look at W and X, I go, is this possible? Well, if W was to be metal M, then metal X could be the other metal over there. What I also have to check is it not possible for it to be Y and Z? So if I look at Y and Z, it could be Y and it could be Z, like this. So this is this is actually not true, because it could be Y and Z, like that. There we go. All right, I'll remove these each time because it's a little bit clearer. So then with B, it says metals W and Y. So we check that, so W and Y. So again, W could take the +1 charge and Y could take the +4 charge. So that's a possibility. And it says not X and Z. If I look at X and Z, I can see that X could be the +4 and Z could be the +1. So that actually is possible, so therefore B is out. C says X and Z. Hopefully now you're starting to see the pattern here. X and Z, again, Z only has a +1 state, so that has to be the +1, but X can still take the +4 state. But then it says not W and Y, same thing. W could be the +1, Y could be the +4. So by process of elimination, we've got D, but let's just prove it. Could it be X and Y? Yes, because we've got +4 and +1, but we could have also had it the other way around, right? It could have been this way. And then it says, but not W and Z. And here, this is also true, because if W were to be the +1, Z does not have a +4 state. And likewise, if Z were to be the +1, W does not have a +4 state to make up the difference. So therefore, D is going to be the correct answer. So then in the potassium salt K2MCl4, the metal M could be which metal, right? Classic Jesse style here. Little typos because I just seem to not be able to pick those up. So it could be which metal. So obviously there's all combos again. So what I would do in this case is just try to determine which ones it is and then match it to my answer. So I'll first work out the oxidation number, because that worked for me last question. And again, it's relating to identifying a metal, so I only have oxidation numbers to go off of. So I use the same method, 2 lots of potassium, which is in the +1 state, plus then metal M, which I don't know, plus 4 lots of chloride, which are in the -1 state. Cancels out to 0. This gives me 2 plus M minus 4 is equal to 0. So therefore M minus 2 is equal to 0. So M is equal to 2 plus. So it has to be able to form the 2 plus state. So now I go, what metals can do that? And I run along this row here and I can see bang, bang, bang. Could be W, X, or Y, but not Z. So I look for my answer, W, X, or Y, but not Z, and then B. So I didn't have to test every single one on that. Then we've got question 3. If metal Y is oxidized, which of the following is not a possible oxidant? Always look out for bolded or underlined words in the questions. So remember that an oxidant in redox actually undergoes reduction. And so remember that in order to undergo reduction, reduction is a decrease in oxidation number. If we think logically about this, if you've got a metal in its lowest oxidation state, then it cannot lower any further, therefore it cannot reduce from that position. So if we look at the lowest possible states, W can go down to a neutral state, X can go down to a 3- state. Now realistically it's a metal. I looked it up, metals can actually be forced into negative states, but it's very, very rare. There was an example of like silver, I think, or something. You can mix it with like a halogen and force it into a slightly negative state. But I've just put it in there for the sake of the question. Y can only go down to a neutral state and Z can go down to a neutral state. So realistically, any of those metals in those specific states would be not a possible oxidant because they cannot reduce. That would be the simplest way to look at it. If it's in any of its higher states, it could still reduce down the table into a lower state and therefore act as an oxidant. So in this case, if we search through, we look at the states of each one. So look at each option, X2O. So this would be 2 lots of X plus a -2 equals to 0. And this would then give me X is in the +1 state when I solve that. Is that its lowest state? No, it could still reduce further, right? And therefore act as an oxidant. If I look at YOH4, that is in the Y is in the +4 state, so that definitely can go a lot lower. This one here, WNH3, so NH3 actually does not change the oxidation number. Now again, I've left this one out of this stem, but I think realistically ACER would probably provide that information, or they'd give a table of values or something as to what the charges are, but threw that in just as an extra trick. So if you got tricked by that and didn't know that, don't worry, just take it as a fact and you can take it with you for future questions. So here it would be like W plus nothing equals 0. So W is in the 0 state, and then you can see that is its lowest possible oxidation state, and so therefore it cannot reduce further. So there's our answer. But let's also look at this complicated one. In this one here, we've got one of those metal ligand complexes. And we can see that sodium, if we're looking for Z, we can assume that sodium is in its standard 1+ state. This is in the 0 state, and there's 5 of them, so they contribute nothing. So you end up with +1 plus whatever Z is in, and then NH3, so +5 lots of 0 adds up to nothing. And then we can just get +1 plus Z is equal to 0, so Z is in its -1 state, like that. And I don't know why I did that. That doesn't even work out. That's not even possible. So there we go. That's actually probably a slight error from me and miscalculating, because I do a lot of these in my head and I probably shouldn't. But doesn't matter because that can't even form a state. So therefore that structure is not even possible. So moving along. Cool. So then question 4, which of the metals can form 2nd degree metal oxides? So we can do a bit of like word association. There was a mention of degree over here, and that was talking about the number of metals that are in the oxide compound or in the compound. So here we're looking for 2nd degree metal oxides, so things that have the form M2O, like that. They can also be M2O3, they can be M2O anything, right? Doesn't matter. As long as it's got 2 metals, then it's a 2nd degree. So this one we really just have to check. I probably wouldn't look at these. I'd probably just work out which ones can and which ones can't, and then make a list and come back. So here if we think about how that actually forms, it comes down to the relative proportion or the relative ratio of charge between the metal and the oxygen. So oxygen is always in the 2- state. So if you need to balance it, it's going to have to kind of cross multiply. So if we look at W, if it's in the +1 state, then you would require 2 W's to cancel out the -2 in the oxygen. So therefore W can form a second degree, right? I don't even have to test its 2+ state. If I look at X, then you can start to see it's actually just down to the +1 in this case. Every time in these states, they would always form a second degree, like this. So immediately, that just means double check which of them can form a second degree. All of them can, from a specific oxidation state. The next one then is how many second degree metal oxides could be formed from the above metals across all of their different states. So we've already got 4 along through here, but we've got to test what about some of the other positions. So we know none of these can work because you can't put a negative with a negative oxide. But if we look at the 2+, you'll find that if you have a 2+ metal, you only need one of them to cancel out the 2- on the oxygen. So these would all form first degree. So these won't work. So we'll cross all those. If we do a 3+, if you've got 3+ and 2-, then you have to do a bit of cross multiplying, right? You need 2 metals to make a 6+, and you need 3 oxygens to make a 6- to cancel out. And so therefore that would make a second degree. So that means that anything, the 3+ also counts. So we've got 4 here, another 2 here. If we look at then the 4+, we'll start to see a pattern that looks like the even numbers don't work, the odds do. So with 4+, if you had M4+ O2-, you could keep the metal and you just have 2 oxygens in that case to cancel it out. So that doesn't work. And then finally 5+. 5+ and 2-, you could do that cross multiplying again. 2 metals to make 10+, and 5 oxygens to make 10-, and that would be a second degree as well. So if we've got 4 + 2 + 1, that gives us 7 different second degree metal oxides are possible based on that information. So you can see, you can start to recognize patterns throughout. And then what is the highest degree possible for the metal oxide? So how many metals can you stack on to an oxygen? So realistically, remember that it's a molecular formula is the lowest possible, well, it's not actually the lowest possible ratio, but you can't just multiply it up. So for example, if you had M2O like this, you can't just go, M4O2, right? In that case, this is the true molecule in itself. So if we look at it realistically, what is the highest degree? It kind of just comes down to the charge on the oxygen. And so since the oxygen is 2-, it means you can only have up to a second degree, but I'll explain why. So because we have a 2-, it meant that as soon as we had a 1+, we had to have 2 of them to cancel it out. But we never had to go to 3, right? Because if you had 3 metals, if it was in a +1 state, then you'd be making a 3+, right? Oxygen can't make 3+ because it's an even number 2-. If it was in the +2 state, then you'd be making a +6, right? So that would be M3, but then you would need 3 oxygens, that's just the same as MO. In that case, you can just simplify it down. So there's no need to make 3. If you had a 3+, we saw that before, you had to have M2O3, so that goes up to a second degree. If we had M4+, we had that same thing, where it was just put 2 oxygens on it, right? So it never actually had to go above 2. Whenever it was an odd charge, you had 2, and when you had an even charge, you had 1. So it was just fluctuating between 1 and 2, and that's it. So therefore, the highest degree is that. Now think about how could you kind of make an alternative to that same question. You could also look at it as what values could N take for a metal oxide, and it could be 1 or 2 as the final answer. And then finally question 7, so a first degree chloride metal ligand complex with a coordination number of 6 forms a first degree sodium salt. Which of the above metals could the metal at the center of the metal ligand complex be? Now that's just designed to just be a really, really confusing question. Let's just break it down. So you've got, first of all, you've got a first degree metal ligand complex. So you've got M and then chlorides, but you don't know how many there are. Then it says has a coordination number of 6. So now you know there are 6 attachments to it. So we're slowly building it. This is our ligand complex. That forms a first degree sodium salt. So when you put sodium in it, because it's first degree, it means you have 1 sodium attached. And there we go. And it didn't say anything about charge, so we can assume that it's neutral. And so then that is everything that we need. And then we're working out what metal could this be. So we have to work out its oxidation number to identify what metal it is. So that means that we've got +1 from the sodium, and then plus metal plus 6 chlorides, which are -1, equals to 0. So +1 plus M minus 6, like this, you get M minus 5. M is in the 5+ state, and then we go over to the table, and we can see the only one that forms a +5 state is Y, and so therefore it's metal Y. Done. And there we go. So hopefully that was clear. It's a very specific type of question. Hopefully I've done it justice and reflected something ACER-esque almost. But again, I have no idea. Hopefully I've done that well. Let me know what you think of the questions themselves and of the explanations. And if you've got any questions, just let me know in the comments. Otherwise, I will see you guys in the next one.